Okay, so let's talk about carbon-13 NMR. And I'm just going to presume that you know about proton NMR, and we're just going to add on to that. So carbon-13 NMR is much less sensitive to the proton NMR. Okay, so you don't get the same fine details in the spectra. You don't get all that multiplicity splitting, and it takes more time to run these NMRs because the abundance of carbon-13 is much less. Okay, it only makes up about 1% of all the carbons. So all the carbon-12s are not detected by this instrument because remember we need those odd nucleons, odd number nucleons for it to work. Okay, so odd masses. Okay, because of this lack of sensitivity, it does not show peak splitting multiplicity, as I just said, to determine neighbors. Okay, nor does it have a signal intensity that is proportional to the number of carbons. So you can't do integration. So multiplicity is out and integration is out. Okay, so remember proton NMR had we had multiplicity, integration, chemical shift, and what's the other one that I'm thinking of? Well, number of peaks, of course. So all we've got left with carbon, so only the number of peaks, and here instead of hydrogen environments, they're carbon environments, and the chemical shift. That's all that we can get from carbon-13 NMR. So less information, okay? So if we want to learn more about the structure of how things are bonded, we get a bit less information from carbon-13, but it still could help us out a bit. Okay, again, trimethyl sulfane is still used for the 0, and our samples are still dissolved in, oh, okay, so your deuterated, oh, that should be CD2. Okay, so double deuterated and double chloride methane, and then the triple chloride 1 deuterated methane backbone. Okay, common solvents. All right. So, oh, okay, so we see this in here, and look at my example here. It's given. Okay, it's going to be some chemical shift. It's not our 0. I'd say the HSC might give you a spectrum without it, okay? But there could be a tricky question that might have you identify that there's one more peak in your spectrum than that that should be there, and you might need to identify that. That's probably the solvent. Pretty tricky though. I don't think they're going to go for that, okay? So here I've got the carbon-13 NMR for, what have we got here? We've got an ester, don't we? And I can tell it's an ester because it's got the ester group in the middle, the carbonyl with the oxygen single bonded, and then the rest of it. So it is, this is your alcohol source. So it's an ethyl. And there's 2 on the carboxylic side, so it's an ethanoate. So I've got the carbon-13 NMR of ethyl ethanoate, and I'll talk about, now let's talk about here, carbon environments. Let's get started earlier on this example, okay. Same thing, we're looking at symmetry of the carbons instead. Could one carbon be interchanged with another? Now here with this molecule, this carbon, this that holds the CH3 on the end, is right next to a carbonyl, and there's not another CH3 next to a carbonyl. So that's one carbon environment. This carbonyl carbon is the only carbonyl carbon, so it's its own carbon environment. This third carbon that they've labelled is its own because it's right next to the oxygen, and it's got a methyl group on the other side. And lastly is this one. So we've got 4. All 4 individual carbons will have their own peak in this one because of the lack of symmetry in this molecule. Okay, so 4 peaks, and look, we've got the 4 there. Why don't we go a bit further and try to assign them, okay? No, let's not go that far. Okay, let's hold on. So the number of peaks correspond to the number of carbon environments, just like the number of peaks in the proton NMR related to the number of hydrogen environments. Okay, so here I've got propanol, notice that the alcohol is over on the end, so that lack of symmetry then causes that each carbon has its own environment, okay? Because they're all differing distances away from that oxygen, okay? But if we change it to propan-2-ol, we've got suddenly a symmetry about here, okay? And so this CH3 that they've numbered number 2 is a CH3 with this kind of ethanol group off it, and this is also on the other side a CH3 with another ethanol group over the other side. So each of these 6 hydrogens you can interchange without anyone noticing. You can do the old swapsy-do when they turn their back. So that's actually one carbon environment, okay? And this carbon in the middle, of course, it doesn't match anything else, so it's its own carbon environment. So we've got 2 carbon environments. So for the 2 isomers, so the 2 position isomers, propan-1-ol and propan-2-ol, it changes their carbon 13 NMR quite differently. So this is one technique that you can tell the difference between 2 isomers, okay? The one on the left has 3 carbon environments, so 3 peaks, okay, 1, 2, 3, like they've got there underneath, and excuse me, the propan-2-ol, because of the symmetry and those 6 hydrogen, sorry, I'm talking about hydrogens, and those 2 carbons can be interchanged. Oh, what a duffer what I said there, the 6 hydrogens. These 2 carbons of the CH3 can be interchangeable, not the hydrogens. So they can be, they're the same carbon environment. So we've got 2 peaks there, okay? And this one's a bit easier. That's belongs with those 2, okay? And the purple one is closer to the oxygen, so it's further downfield, okay? And let's go back to the left-hand side one. Oh, yellow's never going to work, is it? I've got a brown. This carbon here is closest to the oxygen, so it's that one peak there, okay? And this second carbon is the not quite as far, so it's the not quite as downfield one. And lastly, in grey, this third one's the furthest away from the oxygen, the more electronegative atom, so it's the furthest upfield, the closest to 0. Okay, let's look at a few more examples here. I've got the carbon-13 NMR for ethanol. There are 2 peaks in this one because there's 2 carbon environments, okay? Because they're differing lengths away. Why am I doing them the same colour? They're different lengths away, different distances away from that electronegative atom. There's not much symmetry there, okay? So this orange one, oh, what a duffer, back. Well, this pink one is furthest away from the oxygen, so it's the furthest upfield, so that's that one there. And the orange one is closer to the oxygen, so it's further downfield, so that one there is representing that carbon. Okay, now we've got ethanol on the right hand side here. We've got 2 carbon environments, that one there that has the carbonyl, and this red one, I'll do it in red, that doesn't, okay? So that carbonyl one is, of course, closer to the more electronegative atom, so it's pretty far downfield, and this red one is pretty upfield, okay? Because it's further away from that oxygen. Alright, oh, that's the one that I just did on the first page, and oh, let's look at this one. This one's got some chlorines on them. Okay, so we got three carbons here, okay? One, that orange one is, well, it's further away from any, well, it hasn't got any chlorines attached, so it's the furthest upfield, I'm going to call it that. No chlorines attached. Number 2 has 2 chlorine attached compared to number 3, so I'll try to stick to the same colour. That blue one there with 2 chlorines attached is the furthest downfield. And then the one on the end has 1 chlorine attached, but it also has 2 chlorine neighbours, so it's kind of in between there. Okay, so here's a textbook for these typical shifts that you're seeing here. So they're kind of rough ranges where you should see them, okay? Notice that the ppm here is a much larger number than the proton ppm. Don't worry too much, okay? So again, no need to remember this one, okay? And I'll get to that soon. Here's just a more visual guide to it, good old compound interest. But in the data sheet, we've got this, okay? For some reason, they haven't put in proton, but they put in carbon-13 NMR shifting, okay, to help you out. So this is from the data sheet, what you'll get in the exam. So there's no need to remember them, and you'll probably have to try and assign them, okay? So there's lots of different ones. You've got your alkane carbons here. You've got, adding on a halogen, you're in this range. If you've got a ketone kind of thing in this side, and then an amine carbon on this one, and then we've got an alcohol and ether we don't really talk about, but an alcohol or an ester in there. And what else we got? Oh, we've got double bonding carbons. We've got the mental blank carbon. Cyanocarbon. Okay, and then benzene carbons are up there. And then the esters or the carboxylic acids are around here, and the aldehydes and ketones are up around 190 to 220, which we saw up here, didn't we? Okay. All right, let's do an example. Probably not something you get in the HSC, but I think it's a good exercise. So we need to predict the carbon-13 NMR spectrum for 2-chlorobutane. And I'm getting you to draw the structure and then put it in there. Okay. What I might do is just do it on this page. Okay. So let's draw 2-chlorobutane. So butane, 1, 2, 3, 4. Meth, eth, prop, but. So there's my butane backbone. And my chloro is on the 2 position. Okay. I'll put it on the left. Doesn't really matter. Okay, fill in the rest with hydrogens. That's my 2-chlorobutane then. And then I'm going to assign how many carbon environments there. Don't let me get confused and start talking about hydrogen environments, because that will be embarrassing. Okay, looking at the symmetry, I've got the chlorine on one side. Okay, so there's kind of like an asymmetry around the chlorine. So I'm going to get different carbon environments. So this carbon here is only 1 away, and it's a CH3. It's different from this. Okay, it's a CH2, and it's 1 away, so it's different again. So they're different carbon environments. Okay, this one with the chlorine is the only one with chlorine attached, so that's a different one. And what's a fourth color? Let's go brown. This one's the furthest away. Okay, so I've got 4 environments there. So I should see 4 peaks. Okay, I might call brown peak 1. Okay, green is peak 2. Pink is peak 3. And orange is peak 4. Okay, so let's look at the shift of those. So let's go back to here. One with a chlorine should be about 10 to 70. That's a large range. Let's just call it 60. So that pink one I'm going to call 60. Okay. So the orange one on the end should be pretty downfield for what it is. It's a CH3 on the end, but it should be kind of probably... See how the range says 5 to 40? It should probably be... Let's do it at about the 40, because it's right near... It's right near that chlorine. And we'll do the green one the same ish. We'll call that 38, okay? And that brown one should be, it's further down. Let's do it halfway in that range. So let's do it at about 20. Yeah. Just making it up. That's okay. It's just an estimate. So we'll do it at about 20. Okay? So we're not going to get any multiplicity. We're not going to get any splitting. It's just the number of peaks and the shift for them. So this is nice and easy. Have we got a scale on here? Well, no, I don't. But that's okay. I can do 10, 20, 30, 40, 50, 60. All right. So I can do 10, 20, 30, 40, 50, 60. I can do my own scale on there. So let's do that pink one at 60, or just below it. Okay, and let's label it 3. And let's do one at 40, the orange one at 40, and let's label it peak 4. Oh, peak 4. Now the height of these doesn't matter. You might have noticed there were slightly different heights, but who cares? Let's not go into that. It doesn't mean anything. Peak 1 was at 20. That was the brown one. So peak 1. And that peak 2, that green one, was close to that 40. So let's do it in there, peak 2. Okay, so there's just my prediction for the carbon-13 NMR of 2-chlorobutane. Okay, let's do butanone. These are the same examples that we did before, didn't we? With the carbon, or sorry, with the hydrogen. Butanone. Oh, that's a terrible, like, I'll do it in black. So, Mr. Roberts, do it in black. It's hard to see green. What are you doing? Put in my hydrogens? Remember, this only had 3 peaks, 3 hydrogen environments. Now we've got, let's have a look. Moving too quick, okay? No other carbonyl carbons, so that's its own environment. There's a CH3 next to it. That's its own one. There's a CH2 next to it. That's different. So, that's its own one. And, oh, yeah, green. That one on the end. The CH3 is 2 away from it, okay? So we've got 4 peaks. Peak 1 in green. Peak 2 in blue. And peak 3 in red. And the purple peak 4, okay? Oh, that purple on it. Anyway, so the CH3 is near an O, so... Okay, so that... the carbon with the oxygen is going to be 20 to 50, so let's call it 40. So that red one is about 40. So that one near it is probably just a bit down. So do the CH3 on the end just a bit below 40. Let's call it 35. So that purple one, let's do the purple one 35, and then the blue one, let's do it 32. Who cares? Doesn't matter about the order there, they're roughly the same. And that other one is further away again, so let's do it down around, what did we do the last one? Maybe about 15 or so, who cares? Yeah, it's just a rough estimate. Let's do it at 15. Alright, so peak 1, oh, we're only going down to 40, 10, 20, 30, 40. Well, that'll do. Okay, so that first one's about 15. So that's peak 1. What do we got next? The blue one, peak 4 was at about 32. Our red one was at about 40. So that's peak 3. And what are we missing? Peak 2, which was the purpley one. That was about 35. Alright. That's all we can do. Past paper questions. Compound X shows 3 signals in its carbon-13 spectrum, so 3 carbon environments. Okay, treatment with X with hot acidified potassium permanganate produces Y. So that's looking like it's an oxidation reaction. Hot acidified potassium permanganate. And also, compound Y turns blue litmus red. So it's an acid. So that's a carboxylic acid. So it's the product of an oxidation that turns blue litmus red. So it's a carboxylic acid. So that must have been, it started from a primary alcohol. Okay, so we must have had a primary alcohol with 3 carbon environments. Okay, carbon X produces compound Z on reaction with hot concentrated sulfuric acid. Okay, so we can dehydrate it. So Z is what's an alkene? I Okay, well, so we've dehydrated it. Which of the following identifies X, Y, and Z? Okay. Alright, so let's look at... Okay, we must have a primary alcohol. Butan 1-ol is a primary alcohol. Butan 2-ol is a secondary. Methyl ethanoate, no. And 2-methyl-propan-1-ol is still a primary alcohol. Okay. It is going to a carboxylic acid. Okay. So butan 1-ol would go to butanoic acid. 2-methyl-propan-1-ol, it goes to 2-methyl-propanoic acid. Yeah, that's good. Okay. And then if we dehydrate it, we're going to but-1-ene and 2-methyl-prop-1-ene. Okay, that all seems to fit. I'm thinking that the 3 carbon environments are going to distinguish what is going on here. Okay, so meth, eth, prop, but-anol, but-1-ol. Even without drawing the hydrogens in, because it's so unsymmetrical, we'd have 1, 2, 3, 4 carbon environments. Okay, so that's not it. Let's look at the 2-methyl-propan-1-ol. Okay, prop, 1-ol, 1, 2. Okay, these two on the left hand side are going to be the same carbon environments. Okay, you can interchange between the two. So 1, 2, 3 carbon environments. So D is the answer there. So with all the other information after that first statement, it could have been A or D. But that 3 signals in the carbon-13 spectrum allowed you to identify, it's not A, it's D. Alright, can have a go at the worksheet, and there's some example from the textbook, and we'll start talking about IR spectroscopy next.